For decades, solar energy has been synonymous with silicon, thick, rigid wafers grown in high-temperature furnaces. But there is an entirely different way to manufacture a photovoltaic cell, starting with a liquid. This chart plots power conversion efficiency over time. The bottom line tracks traditional silicon, which is largely plateaued after 30 years of optimization. The vertical line is perovskite. In just over a decade, perovskite cells have climbed from an initial 3.8% efficiency to over 25% today, matching silicon's absolute peak. This rapid scaling is driven by a class of materials called organic-inorganic hybrid perovskites, or OHIPs. They share a specific crystalline structure defined by the chemical formula ABX3, where organic and inorganic cations are bound together by halide ions. This exact atomic arrangement provides massive physical advantages. OHIPs have a highly tunable bandgap and immense carrier diffusion lengths. When sunlight hits this lattice, it generates excitons, electron-hole pairs, with high efficiency. A perovskite layer, just 1 micron thick, can absorb as much light as a silicon wafer hundreds of times thicker. But the very trait that makes OHIPs exceptional absorbers creates a glaring vulnerability. The perovskite lattice is held together by weak ionic bonds. It is physically soft. Expose it to ambient moisture, heat, or prolonged ultraviolet light, and the structure quickly degrades. Generating electrical charge within that soft lattice is only half the process. To output power, the cell must extract those separated electrons and holes to an external circuit before they recombine. If they recombine inside the material, the energy is permanently lost as heat. Achieving commercial viability is no longer about improving the perovskite absorber itself. The core physics there are largely solved. The actual engineering bottleneck lies at the boundaries, the electron and hole transport layers, tasked with pulling those charges out. To extract charge from the absorber without destroying it, the device requires strict directional filtering. It must pull electrons in one direction and push holes in the exact opposite direction. In this energy diagram, the central perovskite absorber relies on strict alignment with the transport layers. Light splits charge carriers down the cascade, generating voltage. But misaligned boundaries create interfacial traps where electrons and holes recombine, destroying the cell's efficiency. Minimizing these exact recombination pathways is the primary method for maximizing both the open circuit voltage and the short circuit current of the device. Efficiency depends on the integrity of this energy cascade, a chemical sequence where the quality of the boundary dictates the performance of the whole. Here is a 3D schematic of the physical device stack. The blue layer directly beneath the gray perovskite is the Electron Transport Layer, or ETL, traditionally titanium dioxide. The jagged boundary where these two layers meet is a primary failure point. Legacy titanium dioxide possesses high electron mobility, but it suffers from natural structural flaws, specifically oxygen vacancies. These empty spaces in the atomic lattice act as the physical traps we saw in the energy diagram. Furthermore, titanium dioxide is highly photoactive. Under ultraviolet light, a photocatalytic reaction triggers, actively destroying the perovskite structure positioned above it. To counter this, the industry is pivoting toward alternative UV-stable metal oxides like magnesium zinc oxide and indium oxide. But simply swapping out the base material isn't enough. The chemical synthesis pathway used to deposit that layer must be altered to prevent the defects from forming in the first place. This diagram compares two synthesis methods. Standard hydrolysis, seen at the top, leaves behind an unstable, uneven sediment. But by utilizing a chelation reaction, adding specific stabilizing additives to the precursor solution, engineers tightly control the atomic bonding. Preventing uncontrolled hydrolysis specifically eliminates the microscopic pinholes and cracks, yielding a dense, highly crystalline thin film that can be laid down at low temperatures. Engineering the ETL is an exercise in damage control, extracting the electrons safely while shielding the perovskite from both UV degradation and structural traps. At the top of the physical device stack sits the hole transport layer. Traditionally, this layer is built from an organic compound called spiro-OMTAD. In its natural, untreated state, spiro-OMTAD is highly resistive. Its oxidation levels are simply too low to conduct positive holes efficiently. The current workaround relies on brute force chemistry. Manufacturers force high oxidation states by blasting the HTL with oxygen plasma or aggressive acidic dopants. This solves the conductivity problem, but introduces a fatal side effect. The aggressive oxidation process bleeds directly through the boundary, decomposing the active perovskite into inactive lead iodide. The modern solution is to engineer entirely new, dopant-free transport materials, utilizing fluorinated organics or inorganic copper-selenium cyanide films. With intrinsic hole mobility, they extract charge rapidly, without hostile chemical environments, extending the cell's lifespan. Achieving long-term stability requires abandoning reactive dopants in favor of chemically inert transport layers that do not wage an internal chemical war against the core absorber. This diagram maps the multifunctional interface layer, or MFIL, a single boundary solving multiple degradation vectors. It optimizes electron transport and near-infrared photocurrent. Externally, it physically blocks atmospheric moisture. Internally, it bonds to the perovskite layers, passivating defects and suppressing ion migration. The real-world impact of this specific architecture is immense. Sustained device efficiency over 21% for thousands of hours, with zero external encapsulation required. The MFIL demonstrates that treating the interface as a dynamic, active component rather than a passive boundary enables the long-term stability necessary for commercial deployment. While MFILs optimize the traditional 3D architecture, some researchers are abandoning the 3D-only model entirely to permanently solve the moisture and ion migration problem. This cutaway illustrates the 2D-3D passivated lattice architecture. By introducing large hydrophobic cations during synthesis, an ultra-thin 2D perovskite layer is forced to grow directly on top of the 3D bulk. This acts as an intrinsic cap, physically sealing the bulk material beneath it. Taking interface engineering to its absolute extreme requires removing the most vulnerable layer entirely. This is the stack diagram for a carbon-based perovskite cell. In this architecture, the expensive, unstable organic hole transport layer is completely eliminated. In its place sits a highly conductive, perfectly inert carbon network. The trade-offs are distinct. While these carbon architectures currently yield slightly lower conversion efficiencies, their manufacturing cost plummets, and their resilience against moisture skyrockets. The technology has evolved. We have moved from simply proving a synthetic crystal can absorb light to orchestrating complex atomic-scale traffic control. The future of next-generation photovoltaics is not about finding a better bulk absorber. It relies on mastering the art of heterostructure integration, where the precise boundaries between materials dictate the survival of the entire device.